I welcome you all to the Spark Research YouTube channel. This is Dr. Veerchandra, Assistant Professor in the Department of ECE, and this is the last session of this electromagnetic theory course. That is the fifth series. So here in this session, we are actually going to take the contents from the fifth unit, and here we will look the transmission line calculator and impedance matching. Particularly, if we look, then we are going to talk about the Smith chart. So let's start the session.
Here is the syllabus for this unit 5, that is Introduction to Impedance Matching, Smith chart introduction, reflection coefficient, standing wave ratio, impedance calculations in a Smith chart. So here we are going to focus particularly on this Smith chart introduction, and by using the Smith chart, how can we calculate the values of reflection coefficient, standing wave ratio, and input impedance. So let's see. So basically, before going to start the Smith chart, we should know about the impedance matching. So first question is that how can we find out the impedance? So with the help of this equation, this is very popular equations, Z in, with the help of this Z in value, that is equal to Z naught into ZL plus ZO 10 gamma L divided by Z naught plus ZL 10 of gamma L. With the help of these equations, we can identify the value of impedance at any point on the transmission line. So this is valid for all, that is lossy medium. A special case, that is for lossy medium, that is gamma is equal to alpha plus j beta. So here alpha is equal to 0. Then in that case, this will be the the lossless equations. So here also we can find out the Z in for the lossless medium with the help of these equations. But also we can find out the tau, that is voltage reflection coefficient, equal to ZL minus Z2 divided by ZL plus Z2, and also S, that is 1 minus tau divided by 1 plus tau. So these are the three major equations that we should remember, very general equations, and with the help of these three equations we can find out the Z input impedance, the voltage reflection coefficient as parameters. But it is it may be difficult for calculations, so we can have the alternate solutions using the Smith chart. Another some conditions here, that is sorted line. If line is sorted, then ZL equal to 0, and in that case Z in, just put the values of ZL in this equation, and then we'll get the Z in values, that will be nothing, J Z naught tan beta L, and tau will be the minus 1 and is equal to infinity. Similarly, open circuited line, here if ZL equal to infinity, again put the ZL is equal to infinity in this equation, and you will get the Z, the ZL will be the J Z not cot of beta L, then tau and S equal to infinity. So with the help of these equations, you may see the equation Z in Z O is equal to Z naught A square. Third, that is matched line, that is Z load is equal to ZO. So in that case, just put the ZL is equal to ZO. So in that case, you can find out the tau L will be the 0, because both are 0, both are equal, ZL and ZO, and then S equal to 1. Just put the value of tau and you will get the value of S. So this is the actually the simple things for short line, open circuited and matched line. Now just let's go introduction to the uh, Smith chart. So here is the unit circle on which the Smith chart is constructed. Unit circle means actually what is the value of the tau. The value of tau will vary from 0 to 1. Like minimum value of tau is possible, that is 0, and maximum is 1. Similarly for S is equal to minimum is 1, and maximum definitely it may be the infinity. So this is called the unit circle. So calculations of the transmission line characteristics such as tau s and z in. So with the help of this, we can find out the values, Smith chart. So we are going to construct. So before going to construct, like whatever the values of the tau is possible, like always it may have the complex numbers. So let's divide it tau r plus j tau I, where tau r is a real part and tau I is imaginary part. So now, since the transmission line may have the different load, different transmission line have, so we are going to construct the Smith chart which will be valid for all type of the transmission line, irrespective of their values of the impedance load. So how is it possible to construct for all? So that is why we are going to normalize the load. So how will normalize? So just divide your load divided by Z naught. So we can write it as R plus Jx, because ZL, that is normalized ZL, may have the real and imaginary component both. So now also tau, that is the voltage reflection coefficient, also can have the real plus imaginary. So with the help of this, now if you remember, tau is equal to what? ZL minus ZO divided by ZL plus ZO. So now replace the value of ZL and then you will get this value Z, that is ZL minus 1 divided by ZL plus 1. Now also ZL from these equations, this will be the one R plus JX, and in this equation ZL minus this one. Now we are going to replace the value in with respect to the tau. So find out the value of the ZL in respect to the tau or in tau J tau I and rewrite it. So once you will rewrite, then you can get the values of real, that is just equate the value of real to real and imaginary to imaginary, and you will get the value of r and value of x. So with the help of the r equations, you will get the these equations, that is tau r minus r divided by 1 plus r whole square plus tau I square equal to 1 by 1 plus r whole square, and similarly with the help of these x equations, you will get these equations. So what are these? So first of all, these real part equations, that is tau r, if we will check, then this is very similar to the equations of the circle. So circle equations may have the x minus h whole square plus y minus k whole square equal to a square, where h and k is the center and a is the radius. So similarly, if we will equate this one, then you will get the center values is equal to what? R divided by 1 plus r, 0, and radius will be equal to 1 divided by 1 plus r, right? So similarly for this imaginary part, we can find out the equation for the real imaginary part. But before that, like if you will plot these equations, since this is nothing, this is the circle, then you will get these type of equations, these type of circles. Like the outermost is for r is equal to 0. How can we construct it? Simply put the values of r is equal to 0 in these equations. Like r is equal to 0, then it will be the tau r minus 0 whole square plus tau I, then divide equal to 1 divided by 1 plus 0, that is radius will be the 1. So that is why radius is 0 to 1, and this is for r is equal to 0. Similarly, put the values of r is equal to, suppose 1, then tau r minus 1 divided by 1 plus 1, that is tau r minus 1 by 2 whole square plus tau I minus 0 and equal to 1 divided by 1 plus 2, that is 1 by 2 whole square. So in this case, this will be the r is equal to 0 0.5, and for r is equal to 1, this is for r is equal to 1/3 1. Similarly, if we'll replace the values of r is equal to 1 2 3 4 5, we can construct the similar circuits with the help of these equations. Okay. Similarly, for imaginary part, we can find out the center is at 1 comma 1 divided by x, and radius is equal to 1 by x. Now again, if we'll put the values of x, as for example, like x is equal to 0, then the center will be, the equations will be tau r minus 1 whole square plus tau I minus 1 by 0 is infinity, and radius will be the 1 by x, that is infinity. So this is for x is equal to 0. Similarly, if we can replace the value of x is equal to 1, in that case we'll get the tau r minus 1, tau I minus 1 whole square and 1 by 1 whole square. So this will be the 1. So since this is your one line, tau I is equal to one line, so you will get these type of circles. So for x is equal to 0, this is your x is equal to 0. For x is equal to half, this is your x is equal to half. For x is equal to 1, this is x is equal to 1. Similarly, x is equal to 2, x is equal to 5. As you know that you will keep on increasing the values of x, the radius is longer, radius is smaller. Actually, now if you will see here, your circle is divided into two parts, and this is the semi-half circle. So that's why, because of this imaginary circles only, we are getting it. And so now finally, let's conclude the Smith chart construction. So if you wanted to construct the Smith chart, in that case, you have to get the values of the voltage reflection coefficient in terms of the R, and if you will see, then it may have the two different types of the circles. For real part you will have these type of circles, for imaginary part you have these type of circles. So once you will get the two different circles, now last step is just combine both of these, that is real plus imaginary, and you will get the final Smith chart. So here is the final Smith chart. Here you will see this is for r is equal to 1, r is equal to 0.5, r is equal to outermost is r is equal to 0. Similarly, this is x is equal to the 0, that is x line. Then x is equal to half, this one. X is equal to 1, x is equal to 2, x is equal to 5, like that. And all the the lower side are the minus, nothing else. Like this is x is equal to minus half, this is x is equal to minus 1, this is x is equal to minus 5, x is equal to minus 10, like that. And one more thing you should remember, the this is P SC is equal to 0. So at this point, since outermost circle is R is equal to 0 and the x-axis is called x is equal to 0, R and x means R is real part, x is imaginary part. So in this case, this is the short circuited one, means here R is equal to 0 and x is equal to 0. Similarly, the right extreme right point here, now R is equal to infinity, x is equal to infinity, that is called open circuit. So P open circuit, and now in between that there is x r is equal to 1 and x is equal to 0. So that is called origin of the Smith chart. I repeat, origin of your Smith chart is at 1 comma 0. So this is origin. So this is by default. So you should remember the origin point, that is r is equal to 1, x is equal to 0. So always if you are going to use the Smith chart, we will consider this 1 comma 0 as origin, and the extreme left side is 0 0 at at short circuited, and extreme right side is x is equal to infinity and r is equal to infinity, that is open circuit. So in between infinity and 0 0 there is 1 and 0, that is origin. So now we'll use this origin to identify all the values, and we'll plot and we'll construct the Smith chart as per the question requirements. So some more points, like if you are moving the clockwise on this Smith chart, you will move towards the generator. Similarly, if you are moving the towards anti-clockwise, it will be the moving towards the load. So mostly we will move towards the generator, that is clockwise. So clockwise, how we'll move, we'll see the some questions on this. So here is exactly, so you should also remember, actually your Smith chart is valid lambda by 2 for 360-degree, that is the length is lambda by 2. If you further, if you wanted to move, then you can divide the lambda. So this is for towards the load, towards the generator, and towards the load. So why are we considering this is load actually, and here is your generator. So this is your ZL, and then if you wanted to find out impedance at Z in at this point, this point, this point, wherever. So if you are moving toward from this load to the generator, then you have to move on the Smith chart in the clockwise. Similarly, if you have the value of Z at this point, and if you are moving towards the load, then you have to move towards the like in the anti-clockwise. So this is the short discussion. Now let's see one question. Question is that suppose 30-meter long lossless transmission line with Z naught is equal to 50 ohm operating at 2 megahertz terminated with a load ZL is equal to 60 plus 40 J. If U is equal to 0.6 on the line, find the voltage reflection coefficient, standing wave ratio, and input impedance. So what is this question? Question is that your transmission line having the length of 30 meter, clear? And Z naught is 50 and operating at this wavelength frequency, that is 2 megahertz, and load impedance is 60 plus 40 J, and the speed of your the transmission line, that is a wave, is 0.6. So first of all, how we solve this using using the Smith chart. So while you are solving this question, first you should have the Smith chart, right? And if you remember the Smith chart, then where is the origin of the Smith chart? So origin is at 1 comma 0. So just find your origin and locate it as a point O at 1 comma 0. So this is your origin. Now after finding the origin, since this chart is valid only for normalized load, so step 1 is to find the normalized load. Here the load is given, the actual load. Here Z naught is 50. So in order to normalize the load, divide your load divided by Z. So if you divide, then you will get the value of ZL normalized, that is equal to 1.2 plus J 0.8. Why are we normalizing? So that we can use a Smith chart without, the why, because a Smith chart is valid only for normalized load. So now once you will get the values of normalized load, now you have to find it. Why, how will you find? So real part is 1.2, imaginary point is 0.8 J. So where is R is equal to 1.2? So if you remember R, so this is R is equal to 1, this is R is equal to 0.5, R is equal to 2, R is equal to 5, R is equal to 10, like that. So this is R is equal to 1 and this is R is equal to 2. So R is equal to 1.2 must be in between 1 and 2. So where exactly the point will be? So this is R is equal to 1, this one is R equal to 1.1, and this is R is equal to 1.2. So while you are solving, please keep your Smith chart uh, uh, in your just solve this question with the help of your Smith chart. So you should do it, just you can pause for the some time and then you can do it along with me. So now, did you got the value of R is equal to 1.2? Just locate it. R is equal to 1.2. 1.2, just you can highlight this circle. Okay, 1.2 circle. Now, what is our target? Next target is to find the complex number, that is 0.8. So where is 0.8? So this is x is equal to 0. This is x is equal to 0. This is 0.5 and this is the 1. So just in between 0.5 to 1 there will be the 0.8. So this is 0.5, 0.6, 0.7 and this is the 0.8. So highlight this semicircle and then the intersection point of R is equal to 1.2 circle, that is this one, and the imaginary circle, that is 0.8, the intersection of this, that you may call it as a point P. So here we got the point P. Now already we have found the origin. So now connect your origin to point P and draw a straight line, and wherever it will cut at R is equal to 0, this you can identify this is a point Q. Now use your scale, put it on this Smith chart and measure the distance OP and also measure the distance OQ. Now take the ratio OP divided by OQ. You will get the value of tau, that is reflection voltage reflection coefficient. So it's very simple to find out the voltage reflection coefficient using the Smith chart. What is the challenge? Only just find out the load and locate it the point P. That's all. And measure the distance OP and OQ. Nothing. This is the point Q is at the R is equal to 0 circle. So that's all. Now also this value is only the magnitude, the angle, just measure it x from this, the the x is equal to 0 line angle. So here on angle is already written, like if you will see the outer part of your Smith chart, so it will be mentioned here is your 60, here it is already mentioned 60, here is your 30 degree, so here is your 60 and here is your 50, so in between 60 and 50 it is your 56 degree. So final value of your tau is how much? 0.3516, angle is 56 degree. So this is the actual value of your voltage reflection coefficient. Similarly, how will you find the S? So just take this OP as a radius. OP radius means your center and the P is your point on the Smith chart, and then draw a circle on the Smith chart. Wherever it will cut on this x is equal to 0, that will be the value of S. How will get the value of S? Simple. Locate your origin, find out your P points, that is ZL, and then draw a circle considering OP as a radius, and wherever it will cut on the your x is equal to 0, that will be the value of S. So very simple. Now final point is that you have to find out the input impedance. So in order to find out the input impedance, first find out where we have to find the input impedance. So in question it is given velocity is 0.63. So find the lambda. Lambda is 90 meter. U by F you can calculate. Then L is equal to 30 meter. So the final, actually the location that you have to find, lambda by 3, that is 720 by 3, so 240. So now from point P you have to move by 240 degree. Why? Because point P is at the load point where exactly you know the value of Z in. Now from this known value you have to find out the unknown points at the unknown point. So where is your unknown point? So your unknown point is at 240 degree. So from this you have to move by 240. So if you will move, then you can get the value of this suppose point G. So just move from point P. How will you move? So consider the OP base and draw the 240 degree angle, and then connect your origin to this r is equal to 0, and wherever it will cut on this S circle, that will be the G value, and that find out the G. How will you find out? So just find out the real part and imaginary part, so that will be the ZL, right? So here Z in is equal to 0.47 plus J 0.035. Now if you wanted to get the final value, this is actually the normalized Z in. If you wanted to get the final value, just multiply by this ZO. You will get this final value, that is 23.5 in plus J 1.75. Smith chart. So first thing, what is the purpose to use this impedance matching? So as you know, if impedance is not matched, that is if impedance is mismatched, that is Z not equal to ZL, in that case we cannot deliver the maximum power. So that is why maximum, in order to maximum power transfer, we must require to match the impedance, that is Z not must be equal to ZL. So suppose if in your transmission line mismatch is there, impedance mismatch is there, then how will you match it? So answer is your, we can use some quarter wave transformer. Here we are going to use the component of your transmission line, that is matching. For this technique we are adding in the series. So here you can see
this is your transmission line, and this is the components that we are going to add in series along with this transmission line. So if I'm going to add, then now because of addition of this the transformer, that is a quarter wave, because of this adding, now what will happen, the impedance will be the matching, that is now we'll receive the z not equal to zl. zl. So how can we receive it? So you can check here. If you remember, this is a formula to find out the Z input. Now further here, put the L is equal to lambda by 4. So L means the beta L. So beta L equal to, further it will be the pi by 2. So here formula is ZL plus J Z naught tan of beta L. This is the for the lossy case, lossless case. So here now beta L can be replaced by this pi by 2, and now replace, and since the bit 10 pi by 2, that is 1090 is very big number, means infinity, so zl can be neglected. Similarly here z naught can be neglected, so zo by zl, that is equal to z in. So z in will be the z naught into z naught by zl. Further now you can see now what is our objective. Objective is to achieve the z naught equal to zl. So now here z naught equal to z in into zl. So now you can the manipulate the z in, and you can make you can achieve this condition, that is z naught equal to z of l. So this is the way to match the impedance in series. There is another technique. If you do not want to add in the series, then you can add this the sorted stub in the parallel. So this is the another technique to match the impedance match. So here how can we do? So exactly the impedance, so admittance, that is the 1 by z, it can be written as your y in should be 1 in order to make z in is equal to zo. So here z in, that is z in by zo, that is the normalized one. If suppose this is 1, in that case y normalized equal to 1. So let's suppose if it is not 1, then what can it be possible? So y may be the have 1, that is if it is 1, then definitely it will be matched, and suppose not matching, means there will be the some components plus jb. Plus jb is the the for unknown transmission line, since we are considering that this is not the impedance matched transmission line. So suppose the impedance is different, means zn is not equal to z naught. In that case y will have the 1 plus jb. So jb is the only reason, because of z naught not equal to z naught. So now further, if we wanted to the remove this jb, then we have to connect the stub in parallel such that ys should be minus jb, right? So we can write y in is equal to 1, that is the case of the impedance matching, and jb, that is actual transmission line admittance, and plus ys, that is the for this admittance sorted admittance, that is parallel one. So we are adding this parallel, that is ys. Why are we adding? Because so that ys should be the equal to minus of jb, so that minus jb plus jb will cancel out, and finally we will receive the y in is equal to 1. That is our target. If it is 1, simply it means that z in is equal to zo, means admittance is matching, impedance is matching. So this is the another technique. Now let's solve one question. So question is here: antenna with the impedance is equal to 40 plus 30 j ohm is to be matched to a lossless line, that is 100 ohm lossless line with a sorted stub. Now we have to find the required stub admittance. So how we'll find out the required stub admittance? So now if you have the Smith chart in your hand, please take it with yourself, and now let's solve it by ourselves. So target number 1, since we know the Smith chart is valid only for normalized impedance. I repeat, a Smith chart is valid only for normalized impedance, and definitely it have the length of lambda by 2. So normalized impedance. So how we'll find out the normalized impedance? So here is the not normalized, normal impedance, that is ZL, and here is your ZO. So first of all make it normalized. ZO ZL is equal to ZL by ZO. So normalize impedance is 0.4 plus 0.3 j. Now locate this point. If you will find, so here is your x is equal to 0, this is r is equal to 1, r is your real part, x is equal to 0, x is equal to 0 0.5, x is equal to 1, similarly like that. So here x, now what to locate? First find out z is equal to 0 0.4 real part. So real part is like this, is r is equal to 1, so r is equal to 0 0.5 here. So 0 0.4 is like at this point, right? Similarly x is equal to 0 0.3 will be also at this point. So r is equal to 0 0.4 is this curve. Which curve? Here, this one curve, right? This is your r is equal to 0 0.4 circle, and x is equal to 0 0.3 circle is this one. This is the semi half circle, which is x is equal to 0 0.3. So draw this one like this and this. The intersection point is your ZL. So this is intersection point. Now what to do? Find out the origin. First find out your location, that is ZL, that is the this point we have already got. Now origin. Where is origin? Always remember origin is at 1 comma 0. So this is your origin. Now connect your ZL point to origin, right, and extend it. And also origin to ZL, consider this as a radius and draw a circle like this. So once you will draw the circle, then this is called the S circle. And now wherever it will cut, suppose this point, so this is your YL, this is the admittance, that is the another that ask in your question. So further check the values here. Now here if you will check, then r is equal to this circle, this is your r circle, so r is equal to 1.6, and j circle, this one is your j circle, so this is your something like 1.2. So this is the final value, that is the stub admittance that we need, a stub corresponding to the stub admittance, right? Now once we'll get the value, this is actually the admittance for this transmission, not the stub. So how we'll get the stub? Stub means actually not the transmission, whatever the stub we are going to add for that. So how we'll find out? So further, after finding this point, now what to do? We are going to draw the one circle, that is the this one, that is S circle, and r is equal to 1. R is equal to 1 means this circle, right? Why this circle? Because the center is at 1 comma 0. So r means the real part circle having the radius of 1, right? So now since we have drawn the two circle, that is one circle is r is equal to 1, this one, and another circle is s, that is the radius is zl, this. So now the intersection point of s circle and r is equal to 1 circle will have the two intersection points. Suppose the intersection points are a and b. So now extend from the 0 a point and b point, right? So corresponding to the a point and b point, now find out the j values, that is your stub admittance. So j plus and lower one is minus. So plus one is, that is the u required, that is the plus jb, and minus jb, that is the for your stub. So if you will include this stub, then it will cancel out your j extra values, whatever you have the complex quantity in your admittance. So this is the extra one that you have in your transmission line, and this is the stub that you can connect in your parallel. So this will cancel out to this one. So finally the stub admittance is your plus minus j 1.04, right? So this way we can find out. Now in your question also we have to find out the length of your stub length. So how can we find? So as we have already found the point A and point B. So what is your LA? That is LA, the distance between the load and your stub. So this is your LA. That is here is your transmission line, and a stub is at this point. So you have to find the distance from this point to this point, right? This is the stub. So exactly how can we find? So answer is that total length is how much? Lambda by 2, always remember, and lambda by 2, and find out this angle. So how much is this angle? So from this x is equal to 0, if you'll found this angle is 62. Here it is written 62. And what about this angle? This is your minus 39. Check it. If you'll check here, this is minus 39. This is in the minus. So total lambda by 2 and minus this region, that will be the full length of your LA. So LA is equal to lambda by 2 minus 62 minus 39. So you will get the final values, this one. Similarly for your stub length, that is your L of B. L of B is your this one, that is stub length. So how will you find this one? So this one, that from origin, like here, x is equal to 0 to this, how much is this? This is your C. Here this is your 62 and this is your 39. So this is your total minus this one 39. You will get this one only. This is the length. So you will get the final L of B, right? Similarly, now we can also locate the point A dash and B dash. This is your A dash and B dash, and corresponding to that, like this is 88 degree and this is also 88 degree. So corresponding to that, 88 and 272, exactly you can find out the distance where you are going to include the stub. So that's all. And then finally S values, like the intersection point of your the radius, that is S radius on this x is equal to 0. So this is the 2.7. So this is the exactly the way to find out all the values. Further also you can, if you wanted to find out the your reflection coefficient, then you can find out this divided by extending this divided by this total wherever it will cut. So this is a technique to find out, to solve the Smith chart. So I hope you. Okay, so thank you to join the session. If you have any doubts, please drop your comments. Thank you.